Welcome. In this session in linear data analysis, we'll use the singular value decomposition, or SVD, to explore a matrix that is ill-conditioned, and we'll also in this session summarize our lecture. Let's switch to MATLAB and take a look at one of these matrices that is ill-conditioned. So here the matrix is, the first column is 1, minus 1, 2, and the second column is minus 1, 1, minus 2.02. And here what I've done is I've negated the first column and then I've offset it by 1%. So one entry is offset by 1%. This is a rectangular matrix. It doesn't have eigenvalues, but it always has a singular value decomposition. When I compute this singular value decomposition in MATLAB, displaying results to 2 decimal places, this is what I get. Is here I get the first singular value is 3.48 and the second is 0.01. Mathematically, this is non-zero, but numerically, I personally would be a bit troubled if I saw two singular values, the first singular value and the last singular value, having a very large ratio, because that would suggest to me that this matrix is not exactly rank deficient, but it's almost rank deficient. And by almost rank deficient, what I mean is that if we try to use A5 numerically, we might find that a small change in an input vector can result in a large change in an output vector. Let's take this ratio using MATLAB, and what we get is we get approximately 427, and that suggests to me that an error of 1% can result in a whole number change of 4 when we perform certain computations. How could we use this singular value decomposition to study the matrix a little more carefully? Well, what this suggests is if we use a cutoff, if we say that we're going to ignore really small singular values and we're only going to study the matrix for the larger singular values, we would say that this has a mathematical rank of 2, but an effective numerical rank of 1. And what we mean is that we could only rely on the first column of the left matrix, that is, the first column of the U matrix, as being a basis for the column space of this matrix. And we can see that this is numerically, what it's telling us is you can tend to ignore the additional information in here because this is almost a 1D space. Well, what does that tell us? Well, if we only have one effective singular value, then that means we should look at the second singular value. This is small, and if we say, well, that is effectively 0, then that means that we can go to the right singular matrix, V, and we can look at its second column. And our analysis is suggesting that vectors that are close to this value, which is very close to being 1, 1, that this is almost the null space of the matrix. And these notions of almost are ones that we would have to explore numerically, and these are good objects for self-study. So there's something very suspicious about this matrix, and the suspicion is coming because the columns are almost multiples of each other. So now, let's turn and summarize what we've learned in this lecture. Some of the properties of the singular value decomposition that we've discovered is for a general matrix that has m rows and n columns and all real entries, that the U vector is an orthonormal basis for the data space, and the V vector, which is the right, is the orthonormal basis for the weight space. The singular value matrix always has real numbers, and it has the same size, that is the same number of rows and columns, as the original matrix had. So the singular values are always real, and the computations are guaranteed to sort them from largest to smallest, and they're always non-negative numbers. The smallest non-zero, if we say that that's sigma sub r, indicates that the rank of A is r. And as we explored earlier in this session, we can say that we can talk about the mathematical rank, which is this definition, or we can talk about the effective rank, which is what we numerically expect to get. The last columns of V are a basis for the null space. And here what we're saying is that we could start at n and then we could back off until we get to r plus 1, and those columns of V would constitute a basis for the null space of A. What have we learned in this lecture? Well, we're now able to determine the rank of a matrix from the singular value decomposition. We can find the column space using the left singular vectors. We can find the null space using the right singular vectors. And we can find orthogonal complements of both of these spaces from the matrix U and V that come from the singular value decomposition.